We tend to think of gravity as the anchor that holds our world together, but for physicists and biologists, it acts as a blinder. It is a relentless, overwhelming parameter that masks the true nature of matter and fluid dynamics. Look at a simple fluid on Earth. Gravity generates four macroscopic forces: thermal convection, buoyancy, sedimentation, and hydrostatic pressure. These macro forces expand and dominate, completely washing out delicate cellular and molecular interactions. The fluid is trapped in gravity-induced noise. By taking experiments into orbital freefall, researchers strip that noise away. They transform gravity from an unavoidable constant into a dial they can turn down to near zero. Without convection churning the fluid, or sedimentation dragging heavy particles to the floor, the chaos disappears. The underlying physics are cleanly isolated. Achieving this state provides the ultimate control experiment required to advance modern science. We first have to clarify what that orbital environment actually is. The term zero gravity is a myth. The spacecraft and everything inside it are in a continuous state of freefall, where the inward pull of Earth's gravity is dynamically balanced by the outward inertial force of their orbital velocity. But that perfect equilibrium exists at exactly one mathematical point, the precise center of mass of the orbiting spacecraft. This schematic maps microgravity levels across the space station. Moving outward, unbalanced tidal forces degrade the freefall. Internal moving equipment and crew introduce high-frequency G-jitter, while external aerodynamic drag and solar photons create a twisting torque on the entire structure. You can achieve a purer freefall by dropping a capsule down a vacuum tower on Earth, but that only buys you about 5 seconds of data. The ISS sacrifices absolute perfection to provide a continuous microgravity environment that lasts for years. The orbital laboratory is a highly engineered, actively perturbed machine. Gathering pure data requires physically isolating sensitive experiments from the very spacecraft carrying them. First, you eliminate hydrostatic pressure, which on Earth creates dense compression at the bottom of a fluid column. In orbit, that crushing weight is removed. Even delicate supercritical fluids, balanced between liquid and gas, lose their extreme compression and rapidly homogenize. Observing this uncompressed state allows engineers to accurately measure the fluid's true high-density and high-diffusivity properties, which are critical for designing industrial waste management systems and cryogenic fuel storage. Heat behaves differently here, too. A fire on Earth draws in cold oxygen and expels hot exhaust upwards. That gravity-driven thermal convection creates the rapid flickering and distinct teardrop shape of a flame. Strip away that convection, and the combustion stabilizes. You get a steady-state spherical flame expanding evenly in all directions, without a single flicker. Isolating a single, motionless, burning droplet allows engineers to map the exact chemical concentrations and temperature distributions inside the flame, data that is physically impossible to capture on Earth, but essential for building more efficient propulsion systems. For materials production, you don't even need a crucible. Without the heavy downward pull of gravity, highly reactive molten metals can be suspended using weak electromagnetic fields, preventing them from reacting with container walls. Stripping away pressure and convection grants engineers access to the precise thermophysical data required to forge high-performance alloys and next-generation semiconductors. In biotechnology, the main adversary is sedimentation. If you try to grow complex tissue in a terrestrial bioreactor, the cells simply sink to the bottom and flatten out, unless you prop them up with a synthetic scaffold. Without gravity, suspended cells use chemical signaling to naturally form a dense, three-dimensional lattice. This matrix-free cultivation produces a pure, functional cartilage analog, solving a major terrestrial hurdle where synthetic scaffolds eventually degrade and ruin the growing tissue. But while single cells thrive in freefall, the macroscopic human body reacts drastically when you remove its gravitational load. The sudden absence of weight immediately disrupts the dynamic equilibrium of the skeleton. It alters the stretch-activated chemistry at the cellular level, turning off the mechanical signals that tell the body to maintain its structural density. The physiological consequence is an unabated bone mass loss of about 1% per month, accompanied by severe muscle atrophy. The nervous system is equally sensitive. The acceleration sensors in the inner ear find themselves completely deprived of gravitational stimuli. Within hours, they adapt through neuronal plasticity, rapidly multiplying their synaptic communication sites to search for a signal that is no longer there. The absence of a downward pull forces living organisms into an immediate biological pivot. They must rapidly rewrite their structural chemistry and their neural pathways simply to adapt to the void. That deep isolation is also pushing the boundaries of fundamental physics, specifically through payloads like the atomic clock ensemble in space. Physicists fire lasers to cool cesium atoms to 1 microkelvin, slowing their velocity for a microwave frequency lock. On Earth, gravity instantly pulls the atoms downward the moment the cooling lasers switch off. In microgravity, the atoms hover, increasing their microwave interaction time tenfold. Extending that window of time pushes our measurement accuracy 1 to 2 full orders of magnitude beyond the absolute best terrestrial clocks. This precision allows us to measure how time slows down or speeds up based on tiny changes in Earth's gravitational height, paving the way for millimeter-level geodesy and new tests of general relativity. Over the last few decades, humanity's relationship with space has matured. We have transitioned from simply surviving the shock of weightlessness to precisely manipulating it. In the early days of Skylab, astronauts were essentially test subjects, carefully documenting the physiological anomalies and fluid quirks they experienced in orbit. Today, massive structures like the International Space Station operate as permanent, highly sophisticated laboratories. They are dedicated platforms engineered for variable control. Microgravity serves as an essential analytical tool used by engineers and biologists to isolate variables that are inextricably tangled together on the ground. By climbing out of Earth's gravity well, we finally clear away the terrestrial static, exposing the mechanical and quantum rules that operate without earthbound interference.